Okay, well, I'm Tom Edgar. I'm director of the Energy Institute and out of the Cockrell School of Engineering. And I was asked by Varun Rai to put together several talks for the student showcase this semester. And since I also have one of my feet is involved with the Pecan Street project, I thought it would be nice to have you guys hear about some of the student projects that are funded actually by the Pecan Street project, or by Pecan Street Inc., as we now say. So, and by the way, there is a background. Josh's first slide refers to the Pecan Street project, and yes, there is a project, but there's also Pecan Street Inc., which has already decided it wants to live beyond a project, one project. So it will continue after the current Smartgrid demo is at least wrapped up, at least in its current form. So the format is going to be each speaker, and I'll let them say just a little bit about their background as they present, before they present, and they'll go for roughly 12, 15 minutes, and then we want to actually have questions after each one rather than saving the questions for the very end. So that way, if your memory is challenged, then this will work out well for you, I think, in terms of being able to remember what questions you want to ask. So, without further ado, I'd like Josh to come up here and talk about the data that we're getting from Pecan Street and how we're looking at it.
All right, thank you, Dr. Egger.
If I can figure out how to turn it off, I would, but you good?
I think they got it. They got it.
Turn it off.
Okay. All right, so my name is Joshua Rhodes. I'm a PhD student in civil, architectural, and environmental engineering. My advisor is Dr. Michael Weber. He's actually mechanical engineering, so I'm a bit of a hybrid between the two. But I've been involved with Pecan Street from pretty much it's starting as a project, and I've been neck deep in the data since then. So I'm going to kind of give an overview of what I've done with the data, and maybe you can ask me some questions about it afterwards. So I'm also going to introduce the project. If maybe some of you aren't familiar with what Pecan Street is, I'll introduce it, and then I'm going to go into what my research has been, some of the stuff I've already done, which includes an energy audit analysis of homes in the city of Austin, and all of the city of Austin. Then I'll look at some work that we did with some measured energy retrofits, some before and afters to actually quantify what statistically saves energy and what doesn't. Then I'm going to look at residential energy use curves, which is what I'm working on right now. And I think this is pretty cool because it was born out of an idea of how do we look at all of this data, because as you'll see, it's quite a bit. And then we'll have the obligatory future work and conclusion slide at the end. So Pecan Street is a one-of-a-kind Smartgrid test bed. It's the first Smartgrid project that's customer focused. There's a lot of Smartgrid projects. There's over 100 of them that have been funded out of the American Reinvestment and Recovery Act. And a lot of them are transmission and distribution utility based. And while those are great and definitely needed, Pecan Street's more focused on what happens on the customer side of the meter. So what happens with what the customer sees and what the utility sees as the customer. So right now it's about 500 home area networks. These are 100% voluntary, so these are people who have opted in to this. There's we're looking at smart electricity, water, and gas, meaning we're measuring electricity at a very fine interval, water and gas as well. Typically they're measured at the monthly level. We're measuring it at 1 minute or better level, 1 second level, now. We have a high penetration of residential solar in 1 square mile, 185 installations, 1.2 megawatts, which is, as far as we know, the densest concentration of residential solar anywhere in the U.S. We're also looking at smart appliances, home energy management systems. These are things that are starting now and will be continuing on forward. And also something that started, Pecan Street just released a press release about actual using dynamic pricing. People have opted into actually taking dynamic pricing, which means that they pay more for electricity at different times of the day, depending on grid conditions and other things, and to assess how people react to those that kind of information feedback. So half of the project, or a little under half or so, is focused in the Miller development area. The Miller development area is the site of the old Austin airport. You can actually see where the old runway was there. And these are the homes that are currently monitored. If I refer to anything as Miller, this is what I'm talking about. This photograph's a little bit dated. They started expanding east and north. But essentially, these are all homes that are built after 2007. They're all green built. And so it's a really nice test bed. Everything is nice and neat inside the home, and it's really easy to see what's going on versus some of the homes that are in Greater Austin, which have building codes from multiple decades. So just in context to the best of Austin, and I did say best on purpose, it's about 1.5 miles from UT, about 3 miles from downtown. So as you can see, it's a big chunk of land that was opened up in a very land-constrained city. There's development all around it, and so the idea is that this development is going to be developed right. And that was one of the stipulations that Austin put on it when they were selling it to the developer, Catellus. So there's lots of different data sets that we're pulling from this project. I've alluded to a few. We are getting information from natural gas meters, electric meters, water meters, and then in a lot of homes we're getting electric subcircuits within the homes. We've actually gone in and installed systems at the circuit breaker level to monitor various subcircuits such as air conditioning, oven, things of that nature. We've also got some indirect assessments such as energy audits and surveys. So it's looking at how can we use all of these data sets which are overlapping, which is typically not what you see. You typically see people have data, but they'll have data on a thing like they'll have smart meter data, but they'll have no other data about anything. The thing that makes Pecan Street cool is we have a lot of data, but it's about the same homes, which makes for a pretty rich analysis. So I want to talk a little bit about some of the early work that I did, which was an energy audit analysis on the residential building stock of Austin. This is or a statistically significant sample of single-family detached homes. Throw that disclaimer in there, because 140,000 homes in Austin, I'm not going to work on them all. But we got about 5,000 of them, so that's a pretty good. And the reason we were able to do that is because Austin has kind of this unique ordinance. It's called the ECAD ordinance, the Energy Conservation Audit and Disclosure Ordinance. If you sell a home that's over 10 years old within the city limits, it must get an energy audit. The idea is to use market forces to increase the energy efficiency of buildings. Hopefully people, when they're looking at homes, will not only look at whether one home has granite countertops or not, but they might also look at the efficiency of the air conditioner and how well the thermal facade performs. And we'll yet to see if that's actually happening, but anyways, the information's there. It's better information. The hope is to address Austin's climate protection plan to reduce peak demand by 700 megawatts by 2020. And to date, the audits has collected 12,000 energy audits for buildings. This is residential and commercial. I've did an analysis on 5,000 residential buildings, but this is the biggest treasure trove of this kind of information that exists anywhere. So our first results reveal that there's plenty of opportunities to reduce peak power demand and energy use. Just inefficiency alone, just inefficient air conditioner units lead to an excess peak power demand of about 205 megawatts. And that's 8% of Austin's total 2010 peak. And if you remember, they're trying to reduce it by 700 megawatts. This is a pretty big chunk of that. Oversized units that are actually too big for the area that they are meant to service, can lead to an excess peak power demand about 41 megawatts. Duct leakage leads to an excess energy consumption about 18%, and 20% excess energy consumption can come from reduced AC capacity, where the unit is not actually delivering its nameplate. It's not cooling the way it's supposed to. So here's a histogram of air conditioners that are actually installed. These are actually taken from the nameplate, and this is what Austin Energy recommends. It recommends an energy efficiency ratio of 12. So everything to the left of that is responsible for about 205 megawatts of excess peak. Now, this is a busy chart, and so I'll try to go through it pretty quick. One of the things we're able to do with these audits, we're able to run an industry standard residential air conditioner sizing technique, which is called Manual J. And what we did we took these audits, the information from these audits, and we're able to figure out what should the homes actually have installed, and that's on the x-axis. And on the y-axis is what is actually installed. Here. The white line, the white solid line, is a 1-to-1 ratio. So if what they have is what they should have, all the circles, which is an individual air conditioner installed somewhere out in Austin, should be clustered around that line. The dotted line is 120% of manual J, because for rounding errors, we're saying anything above, because you can't get like 4.57 tons of refrigeration. You can get a 4.5 or you can get a 5. Saying anything, what we said for our analysis was anything above 120% we're calling oversized. The dashed line is 75% of manual J calculation, which is the sizing calculation, because there's even studies that have shown that the industry standard actually does oversize some, and that about 75% of what they say should go in is actually adequate enough to meet the load. So this is where we get 41 megawatts of excess peak, and interestingly enough, if we actually upsized or brought up units that seem to be underperforming or not able to meet the load, it would actually add about a megawatt of peak power demand to the grid. So ducts are notoriously leaky. This is not a surprise for anyone in this industry. Austin Energy recommends that anything above 10% get sealed, because typically your air handling, your duct system run in the attic, and so if they're leaking, they're just leaking cold air into the attic, and that's not doing you any good because you're actually paying for it. And you can see from other studies, we're kind of on the low end, but still pretty much the same. And so all of these that are over to the right side of 10% are what on average lead to about 18% excess energy consumption, because 18% of that is actually going into the attic. So air conditioners are operating under capacity. What they did was they measured how cold could the air conditioner get the air. And most of them are operating under capacity. They're not operating to what they should be. Now, this could be from a host of different things. This could be from an improper refrigerant charge, so the working fluid inside the system is actually leaked out and it's not able to provide the cooling, or it could be a fouled coil. It could be many things. But these are things that just waste energy. They just use more, and one visit from an HVAC consultant could really help a lot. Anyways. So now I'm going to move on to some work that I've been doing recently, and I've actually I've updated it, but I wasn't able to put it on here. So if there's any questions, maybe we can go into that. But some of the homes that some of the residents, as part of this project, as part of getting an ECAD audit, or as part of getting an audit that Pecan Street provided, opted to undertake retrofits, and the retrofits included solar shading to windows, air sealing the house, etc. This is a list of things that Austin Energy will rebate, so it's not surprising that most of them did what Austin Energy will rebate, because they get money back for them. And so what we found was that this is using real measured data. This is, and you might think that, we would know that, but actually no one really has this data to kind of measure this stuff. And so, air sealing, which is sealing around plumbing penetrations, weather stripping around doors, basically keeping the outside air outside and the inside air inside, upgrading HVAC equipment, more efficient equipment, sealing ducts, again, like I talked about how they're notoriously leaky, just sealing them resulted in significant energy savings. So did attic insulation, but the way that Austin Energy's rebate does, they only rebate up to R38, and so the degree of certainty was quite a bit lower on that regression. It was normalized by heating and cooling degree days to make sure we take in account for weather effects. And but one of the interesting things with these, the results of this reinforce the energy audit results, which I think is pretty cool. It's nice to have validation and stuff. So we also looked at basically like what are the drivers of energy use in a home? Like what can we show from this data are the drivers? And so we looked at year built, home size, number of kids and adults, thermostat set points, energy and water IQ scores, which I'll explain in a minute, and income. And some things were expected, although some were more interesting. So year built had a negative impact, i.e. newer homes use less. That makes sense. Size and, I should say size of home, not the size of adults and kids. That doesn't matter. We didn't look at that. But anyway, so size of home, the number of people in the home had a positive impact on energy use. Again, not surprising. Income actually had a negative impact. When controlling for all the other things, for size, for quality of home, income actually had a negative impact. People who have higher incomes were using less. And then energy and water IQ had a negative impact. And this is, I think, is pretty interesting. What we did on the survey for a lot of these people is we ask them order of magnitude questions about how much energy does a home use, how much power does a home demand, how much water does a person use per day, and actually higher scores on these quiz questions correlated with less energy use. So that's pretty interesting because it's a lot easier to do education campaigns than it is sometimes to go in and actually fix something. So the old knowledge is power thing, or the power use reduction, either or. Not sure which one, but. So now I'm getting into some stuff that I'm actually that I'm currently working on, and I think is pretty interesting. This is kind of born out of trying to figure out how to wrap my mind around all the data we've got. At the last count, there was 2.95 times 10 to the 9 data points in our database. So that's a lot of data to kind of wrap your mind around. And here's just a small sample of it. And if you can make sense of that, great. I can't make sense of what that looks like. But you can. So what each one of these lines are, each one of these lines is a home, and this is a summer average curve. So I took June through August, averaged hour on hour, and got an average profile for each home. And you can kind of see there's some things, like there's some stuff going on here. These are going up, but these are pretty close together. And there's some stuff going on here in the morning. Not sure exactly what, but there's some similarities, but it's kind of hard to see. And how do you parse that out? So one of the things I'm using right now, and this is preliminary, I've not finished this yet, is I'm using what are called clustering techniques. Basically what I'm doing is I'm taking these profiles, I'm normalizing them, dividing by the maximum amount of the maximum number, and then because I'm interested in shape. I'm not as necessarily interested in magnitude, that'll come later, but I'm interested in shape. So I take these, and once you do that, I have a 24 valued vector. If you have a vector, you can find the distance between any two vectors. So I use a clustering technique that actually forms centers, iterates on, and then groups clusters into groups. So I go from this to something that looks more like this, something that's a little more intuitive. You can actually see that these actually kind of make sense. Now they're not perfect. Clustering is not a perfect technique, but this is just an example that there might be some characteristics, some variation in profiles. You can see the same thing in winter. Although the clusters are looser, they're not more tight. These are more driven by human behavior, not necessarily weather-driven events. So there's a little more noise in the system. So what am I going to do? So one of the things we can do is you can actually take these profiles, and if we know their probability, if we know the density of them, if we have those and multipliers, we could actually simulate as many homes as we wanted. And some profiles might be more desired by utility, some are cheaper because electricity costs different at different times of the day. So some profiles are cheaper, and some might be less carbon intense. Also want to see do audit and survey data indicate what profile you might have, what cluster you might be in, because that would be really interesting. Instead of having to measure, we might be able to estimate. Certain aspect like these efficiency upgrades or retrofits might actually change the shape of profile. We often think of reducing energy use. It might just pull the whole curve down, but it actually might change the shape. So that could be interesting. It could actually increase or negate some savings depending on what savings means to you. And some technologies might be more effective with certain profiles. Those are some things we're looking to test. So my conclusion, there's vast potential in the residential sector for power and energy reduction. Some measured results indicate what might make sense. Education seems to play a role in energy use, which is cool because I've been in college for 10 years and it's great. The clustering might be a helpful data analysis tool to view large amounts of data in this space. So I'd like to thank Pecan Street, Doris Duke Foundation for funding me, UT, Dr. Weber is my advisor, Charlie Upshaw, who I work with, Dr. Edgar as well, Texas Advanced Computing Center, who provided our computing power to do a lot of the stuff, and then Austin Energy. Thank you. Yes? Oh yeah, use the microphone.
Josh, interesting stuff. The question is about the last data sets we were seeing, the representative power
Sure.
profiles. Do those represent all Austin residents or all Mueller residents or who are participating, or was it some of both, or what were we looking at?
So there's a lot of people in Miller, and there's also another cohort that's just as large that's in the Greater Austin building stock, and it was a conglomeration of those. It was the ones that I had good data for at the time when I was doing it. But yeah, so they're yeah.
Second question. I live outside the city limits but have 4.1 kilowatts of PV and solar thermal, no natural gas, no smart water meter.
Sure.
Am I of interest to Pecan Street?
I mean, I think they're always looking for volunteers, especially with a solar thermal system. I know that there's interest. There's definitely researchers that have interest in that. So I can give you my card and we can talk offline. All right. Anyone else? Yes.
I had kind of a general question. I came in a little bit late. I was wondering about the value in reducing consumption, other than just the climate initiatives or whatever. So, I mean, I guess presumably, you know, a lot of the upgrades and different things that people have that can reduce their power, they would do if they found that it was beneficial, that it was a good trade-off between capital cost and electricity savings.
Yeah.
I can also see where there might be value to the utilities, but if that was the case, then why aren't the utilities engaging in these projects and doing this work themselves? So I guess I'm just wondering who's benefiting and why aren't they paying for it or doing these things?
Well, it kind of depends on who you ask. So why would an electric utility want you to reduce overall usage? I mean, that's how they make their money. Like, you know, they sell a kilowatt hour, they make, you know, however much cents they make. The price of electricity is different at different times of the day, especially in the summer. And on average, it's somewhere around $20 a megawatt hour, which is about 2 cents a kilowatt hour on the wholesale market. In the summer, sometimes that can jump all the way up to $3,000.
That's on ERCOT, correct?
Yeah. Austin. Yeah, but Austin is, but Austin is subject to that. If they can't meet the demand, they have to go buy power on the market. You know, they take a pretty big hit because they're selling it an order of magnitude less than they're having to buy it for. And the thing is, if they can off-put energy, if they can not have to sell to their own customers and sell on the market, then they can make a lot more money that way as well. So it depends on who you ask. Homeowners want to reduce kilowatt hours total. Utilities are probably going to want to shift the demand around. And so it's kind of this conundrum.
So are the utilities interested in doing research in these areas and learning more about how to shift peak loads and that kind of thing?
They're definitely interested in learning how to shift loads, and Robert will talk about that in the next slide. Yes?
Just want to make sure I understand the regression. The dependent variable is electricity consumption or energy consumption in general?
Yeah, there were two different regressions, and I'm sorry I was going really fast trying to get through. The first one was a panel regression on daily energy use for multiple homes, and the second one was just a simple multiple regression on yearly energy use.
So it's energy including all kinds of sources.
Yeah.
And so I think my second question is it possible that you can include some profile groups, as you did in the last step in the regression analysis, to see which group might be potentially more energy efficient?
Yeah, and that's one of the things. I'm using a thing called logistical regression to see the probability of being in a certain cluster. I can tell you that these people are more likely to work at home than these people. You can kind of tell based on the profile. Just these people, they have a little bit more. I mean, you can kind of see it, but it might not be intuitive. But the survey results indicate that these people work at home more than these guys and these guys. So that's as far as I've gotten so far on that.
Okay.
But sorry.
It's okay. Yeah. Thank you.
All right. Thanks, Josh. So next, we got Josh referred to the work that Robert Pierce is doing, and he's really interested in storage for intermittent power production like we have with solar. So, Robert?
Good evening, everybody. It's a pleasure to be here to be able to speak with all of you tonight. Am I good? My name is Robert Ferris, and I'm a third-year graduate student in the Department of Mechanical Engineering. And like Josh, I also work for Dr. Weber, and I've been working on Pecan Street and smart grid research here at UT for a number of years. Today I'm going to talk about the electric grid. I'm going to discuss the design of the grid and some of its weaknesses, and then talk about the research I do on a technology called community energy storage used for an application called islanding. Like Josh, my research is part of Pecan Street's large smart grid effort that's happening here at UT, but I specifically study energy storage, and I look at how we can use energy storage to help reduce the cost of electricity and integrate renewable energy, and also make the electric grid operate more reliably. And one energy storage technology that I've been looking at for some time is community energy storage, which is essentially a 25 kilowatt hour battery system located at the residential transformer level. The specifications for community energy storage have been developed by a number of large electric utilities and other companies over a number of years under the auspices of the Electric Power Research Institute, or EPRI, which is based out of Palo Alto. Some applications that community energy storage can serve is things like load shifting, essentially charging when electricity is plentiful and then discharging when electricity is scarce. Islanding, which I'm going to talk in detail about in the second half of this presentation, and also applications like local power system control. And so I'll talk about islanding more in the second half, but first let me talk a little bit about the design of the electric grid and some of its inherent weaknesses. So today the electric grid has a centralized architecture. This is because of traditional economies of scale. It's conventionally been most inexpensive to produce electricity in large quantities in a nuclear plant or a coal plant, or to a lesser extent a natural gas power plant. And so because this electricity is generated in large quantities, usually far away from the people that actually use the electricity, the voltage is stepped up at a transformer so that it can be transported over long distances on transmission lines. And then later, once the electricity is transported over long distances to the people that are using the electricity, the voltage is stepped down at a transmission substation, and then the electricity is eventually delivered to commercial and industrial customers and also residential users of energy. Because transmission moves so much electricity at one time, transmission is usually built with redundancy, meaning that if one transmission line goes down, the grid can still operate as normal. But conventionally, it's not economical to build redundancy into distribution lines. And so because of this, any small failure downstream of this transmission substation could potentially lead to a blackout or an electric outage for thousands of utility customers. So because of this, in the centralized architecture of the grid, distribution level outages really aren't uncommon. And so what I wanted to do is I wanted to look into how often we face outages here in Austin. And so I looked for a public record from Austin Energy of historic outages. Well, I couldn't find that very easily. I guess it's not surprising that they don't make that readily apparent on their website. But I do follow Austin Energy on Twitter, and they often tweet about outages. So I looked at their Twitter feed to see what outages have been occurring over the last few weeks. So just 2 weeks ago, we had a pretty large outage here in Austin, the Koenig North Loop area by 2222, and that affected about 1,500 customers. So I'm sure Austin Energy got a bunch of calls in their control room, and some red lights started flashing. They sent out some utility trucks to figure out what caused the outage. Well, after the crews investigated, they found out that a tree limb was hitting a power line, and that led to 1,500 people losing power. And then a few weeks before that, we had over 8,000 customers here in Austin. I don't know if you all remember this. From the extreme winds we had, there was actually some pole fires caused just not far away in West Campus by the extreme winds and some transformer failures. So just wind led to an outage that affected 8,000 people. And then a couple months before that, we had an outage in the South First Street area caused by utility pole fires, again, similar to the one that I mentioned that occurred in West Campus. And so I guess my point is that distribution level outages really aren't an uncommon occurrence, and this is because of the way the electric grid is designed right now, with power being produced centrally and then delivered over long distances to the people that actually use it. But nowadays we're seeing that the grid is growing towards a more distributed architecture, and this is because of the rise of solar photovoltaics. So rooftop or solar PV or photovoltaics is usually built on the roofs of people's homes or on the roofs of businesses. And so this means that the electricity generator is located literally right on top of the people that are using the energy. So this has the potential to make the grid stronger in the future. Let me talk a little bit about kind of the rise of PV that we've seen over the past few years. And so the National Renewable Energy Laboratory tracks the installations of residential PV systems and utility-scale PV systems using what they call the Open PV project. And all this data is crowdsourced through utility incentive programs and just individuals. And so we can see there are currently thousands of PV systems operating in the Sun Belt areas where there's lots of sun, and it's usually more economical to build a PV system. But also notably in the Northeast, which was recently really severely affected by Hurricane Sandy, where we had hundreds of thousands of people losing power for weeks. This is because you might say, oh, well, it doesn't look like there's a lot of sun up there in the Northeast, but they do have generous incentives that make building solar PV appealing to homeowners. So with the rise of PV that we've seen over the past 10 years, the price of photovoltaics has also gone down. So you can see this is the average installed cost, and again, this is crowdsourced, so this is what people actually paid for systems on their homes. The average installed cost of a system in dollars per watt has dropped to about $6 in 2012. And this, you know, as the price decreases, more people are going to be installing photovoltaics. So let me talk a little bit about, in order to kind of analyze how this rise in distributed generation and the transformation of the grid from a centralized architecture to a more distributed one affects the grid's reliability. And in order to do that, I'm going to talk about how photovoltaics integrate with the electric grid today. And so this is, you know, maybe a typical neighborhood, for example, like in Miller here in Austin, the neighborhood that Josh referred to in his presentation. It's a modern neighborhood with a pad-mounted transformer and a number of homes with solar photovoltaics. Well, the way the solar panels integrate with the electric grid is when it's especially sunny out, they might be producing excess electricity, more than these homes are using, especially if people are at work. And that excess electricity, to prevent an overload, is sent to the rest of the grid, where it's used by, you know, thousands of other electricity users that need energy at that time. If a cloud rolls over and all of a sudden solar PV output drops, then additional electricity is brought in from the rest of the grid. And of course, at nighttime, when the sun's not shining, all of the electricity that serves load in these homes comes from the external electric grid. Well, the problem with this way of doing things, so the lights are on no matter what. That's the point, right? Thanks to the connection with the rest of the grid. Well, the problem with this way of doing things is that if we have an outage caused at the distribution level, like I referred to before, then if it's sunny, these solar panels might be producing excess electricity, and they don't have anywhere to send that electricity, so they can't stay connected to the grid without causing an overload. And if it's cloudy, there's nowhere to get additional electricity from. So the solar panels can't connect to the grid without providing unreliable power, essentially, that would damage the devices in people's homes. And so the point is, with the rest of the grid cut off, there's no way the solar panels can provide firm electricity to these homes, and so they have to disconnect from the grid, and the lights stay off no matter what, with current codes and regulations surrounding solar PV. But now consider if we were to add a community energy storage battery at the residential transformer level. If we had an outage upstream, this battery could actually, so this is what's called islanding, it could island these homes and create a small microgrid, and the battery can work to buffer these distributed generators, the PV, with the connection between those and the load. So when it's sunny, excess electricity can be put in the battery. When a cloud rolls over, the battery can make up for shortfalls in PV electricity. And the lights can stay on and the PV can stay connected to the electric grid and actually be useful in the case of an outage. At least until the sun goes down and the PV output drops and the battery's energy is finally depleted. And at that point, the lights have to go off and the islanded microgrid has to shut down. So what I wanted to do is I wanted to analyze how long a community energy storage battery with the specifications that I mentioned in my previous slide could power downstream loads for outages occurring at various times of day. So let me talk about how I do that. Well, in order to do that, I need to know the instantaneous electric load on the battery. So how much are all those homes using at the time of the outage? What level of photovoltaic electricity generation is available after an outage? And also, what are the capabilities of the battery system to move around electricity in real time? And how long can it power downstream loads before it's empty? Well, Pecan Street's data, which Josh discussed just before me, really gives me a perfect idea of how much the level of electric load in real time and also the available level of PV generation in real time. So this is data for one home from August 5th, 2011. The red line is electric demand. You can see that's shooting up and down as the air conditioner cycles on and off, especially on a day like August 5th, which was very hot. And the PV generation has a bell shape peaking around 2 p.m., indicating that this is a home with south-facing solar panels. So this is one home. A community energy storage battery and a residential transformer would typically serve around 7 homes. So this is 7 different homes on the same day. You can see the combined, and this is net electric demand. So this is power load minus photovoltaic generation. So you can see it goes negative in the middle of the day, indicating that the panels are producing more electricity than the homes are using. And it peaks around 8 p.m. once PV production has totally dropped off. And so Pecan Street's data gives me a really perfect idea of exactly what the load on a community energy storage battery is in the case of an outage. In order to describe the capabilities of community level battery, I used a behavioral circuit model of a battery. And I picked this model because it has 2 components that are really important for my application. It has this battery lifetime circuit, which essentially acts as a state of charge estimator and tells me exactly how long we have until the battery is empty. And also this voltage current characteristics circuit, which tells me exactly how much power the battery can deliver before it runs out of energy. And so what I did is I used this model of community energy storage with the vast data set that Pecan Street's collecting from here in Austin, and I simulated thousands of different hypothetical outages. And I used these outages to show how long a community energy storage battery could power downstream loads, or what I call its islanding lifetime. I simulated outages from August 2011 to February 2012. I assumed that the battery powered 7 homes in the case of an outage, and I considered cases where all of the homes had rooftop solar panels and a case where none of them did. So let me show you what the results look like. So like I mentioned, the key metric that I wanted to return for my simulations was the islanding lifetime of the battery, or how long we have until the islanded microgrid has to shut down. And so that's on the y-axis here. And I examined how that varies for outages at different times of day. So the time of the outage is on the x-axis. So first, let me show you the results that I collected from residential energy use data from August to September 2011. So these are summer months, and also during one of the most extreme summers in U.S. history. So these are the results of the hundreds of outages I simulated in August and September. As you might expect, the lifetime of the battery is highest around 4 in the morning when most people are asleep and not using any electricity, and it's also rather cool. Well, relatively, but the lifetime of the battery is a minimum around 4 p.m. when it's blazingly hot in August and September in Austin. And so I'll highlight the range of all the, this is for the case with no solar. And so I'll highlight these data points in red, and the mean looks something like this. So on average, the battery can power downstream loads for about 1 to 3 hours based on the time of the outage in summer months. So now let me show you the results for the case with photovoltaic panels on the roof of the homes. So these are all the outages I simulated for the PV case. You can see there's a lot more scatter because there are days when there's no solar production available, or relatively little, and there's days when there's a lot of solar production available. I'll highlight the range in green and then show you the mean. And so we can see on average the photovoltaic panels really significantly increase the lifetime of the battery and the lifetime of the islanded microgrid, which makes sense because we're adding distributed generation to this system. And so now I'm going to scroll through time, and I'm going to show you the results for the fall. And so this is October to November 2011. And we can see the whole graph's been shifted up a bit. That's because the cooling load has decreased significantly because the climate is isn't as hot. But at the same time, we still have plentiful solar resources here in Austin, and so I really observed some incredible lifetimes for the microgrid in the fall, peaking around 21 hours, and on average, the PV could power the homes for over 12 hours for an outage occurring around 6 in the morning. And now moving into the winter, we can see there's less of a difference between the photovoltaic case and the no photovoltaic case, and this is because of winter solar patterns where we have less solar power production available in the winter. But at the same time, there's still a big difference on average between the photovoltaic case and the no photovoltaic case. Now finally, this is the combined results. So we can see without PV, we should expect a community energy storage battery to be able to power downstream homes in Austin for maybe like 3 to 5 hours, 3 to 6 hours. Adding PV really significantly increases this, especially for outages in the morning, increasing the average to over 9 hours. And so what I wanted to do is, after doing all these simulations, using Pecan Street's data, like Josh had mentioned, that have been collected with billions of data points sent to TAC, and then I analyzed them on my computer, I wanted to do a sanity check and compare it to real-world observations and see how my results compared to to historical records, basically. And so what I did is I looked at what's the minimum lifetime that I observed for this community level battery. And the minimum I observed was 42 minutes for an outage occurring at 4 p.m. on August 28th, 2011. And when I look back at weather records, I saw that Austin broke the all-time weather record on August 28th at 4 p.m. And so that kind of really was a good sanity check on my simulations and also on Pecan Street's data. And so finally, let me conclude. So my first conclusion is that the high-resolution residential energy data that Pecan Street's measuring really permits unique research like I presented today. Without knowing the actual load on the battery, I wouldn't have been able to simulate it. I wouldn't have been able to show how the lifetime of the battery varies over the day. And so Smartgrid data really allows us to do some unique research on emerging energy technologies. And based on my results, it's clear that rooftop solar panels really significantly increase the islanding lifetime of a battery, especially for outages occurring in the morning. And so what this means is that the presence of community energy storage really increases the value of solar panels, which a number of utilities have already invested heavily in the case of an outage, turning them from something that has to totally disconnect from the electric grid into really firm, useful, local energy production in the case of an electric outage. So in the future, I'd like to keep exploring the synergy that exists between distributed solar panels and distributed energy storage. Look at applications like how energy storage can correct power factor anomalies that occur due to PV, and how energy storage can firm solar generation and potentially shift solar production to times when the price of electricity is highest and energy is most valuable. I'd like to acknowledge UT Austin, my advisor, Dr. Weber, Pecan Street, who sponsored this work, and then the U.S. Department of Energy Smart Grid Demonstration Program, and also Dr. Edgar for inviting me and advising me on this research. All right, well, thank you very much. You want to do questions now, or?
Well, thank you for your presentation, Robert. You may have done this, and I wonder, like when presentations happen, and maybe this was brought up, but do you know the relationship between the most frequent outages that Austin Energy has, whether they're in the morning or in the afternoon, and what time of year they are relative to your normalized curves?
No, it's not yet, but that is something that I'm really interested in analyzing. And so if we go back to this graph, I'd like to look at when outages occur, but also how long they are. And so if I find that most frequently outages are about an hour in duration, well, that would mean that a community energy storage battery could probably totally eliminate all of those outages. And so that's one thing that I want to look at, is basically how long is the most common outage, and then also when it occurs, and when does that correlate with the availability of PV electricity.
Yeah, because that would give you a cost of, investment return, or prioritizing those kinds of investments.
I was just curious about the approximate cost of the storage units that you examined, just as a ballpark number.
Yeah, sure. It's around, for a lithium-ion battery system that is 20, they call it a 1-hour system, meaning that it can discharge for 1 hour until it's empty. It's approximately, I think it's around $2,500 a kilowatt.
How much would it be per household?
Well, so it depends on the size of the battery, so it depends on what size battery is appropriate for a household, and that's not analysis that I did for this presentation. I mean, a community level battery would be 25 kilowatts, so it would be 25 times $2,500. But when it comes to the actual, and this is something that I do research on that's external from this presentation, when it comes to actually, I guess, making up, trying to maximize the profit you get from a battery, in reality would probably be used for something like load shifting or shifting PV generation routinely, and then only provide backup power in the case of an emergency. Right, and so this isn't kind of a routine economic application. It's really just an additional benefit that the battery has from being there.
Okay, let's move on.
Thank you.
Robert. So now we're going to
Nice job.
focus a little bit more on the building side, and Steve Bourne is going to do the final presentation there.
Hi, my name is Steve Bourne, and I'm a PhD student here at the University of Texas. I'm in the Civil, Environmental, and Architectural Engineering Department under Dr. Novoselic. And what we're going to talk about today is thermal storage and how it relates to intelligent grid communications. First of all, one of the things we're trying to do with the thermal storage is to reduce our peak energy use. There's a lot of benefits that come out of reducing peak energy use. One of the things that we get is improved generation efficiency. We can use our base load power plants more efficiently and eliminate some of the peak electric generating systems that actually produce a lot of pollution and cost a lot of money to run. It also allows us to reduce our overall energy costs for the same reason. We're able to use more efficient equipment. If done with grid-aware applications, we get another benefit. And a grid-aware application would be something that we have devices that can communicate with the electric generation facility and make determinations about whether they should run or not run or how they should run. And by using, one of the things that happens as we're moving forward, we're changing the way we generate electricity. We're starting to deal more with intermittent sources. And as we deal with intermittent sources, we start introducing random variability in our availability of energy. And if we can have a way to deal with that variability in our energy supply, we can gain additional benefits. So what we're trying to do with the grid-aware applications is to provide a means of dynamically altering our energy use as we need to. And as we develop more wind and solar or wave or other type of renewable intermittent energy sources, this will actually play an important role, our ability to moderate our energy use on demand. One of the ways we can make a difference in peak energy use very quickly is in looking at our cooling loads. Cooling loads amount to about 11% of the U.S. electric use, and that's overall. In summer seasons where we have a high air conditioning use, it's actually much higher. So if we can come up with ways to reduce our cooling load, we can significantly reduce our peak energy requirements. One of the ways we can do that reduce our cooling loads, are by using phase change materials integrated into our building systems. What these phase change materials are materials that during the course of their use, they change their phase from solid to liquid, liquid to solid. And the benefit to using phase change materials is that when they change phase, they can absorb or release large amounts of thermal energy at a relatively constant temperature. So it's ideal material for use in cooling or thermal load applications. By putting phase change materials into our building structures, we can reduce our peak power demand. We can also use smaller mechanical systems because instead of having the mechanical system have to deal with peak loads, we can have it deal with average loads and run more frequently. So we can have smaller, more efficient mechanical systems. And we can also create lightweight buildings that have a large thermal mass. Instead of having to build a large concrete structure to give a building a sense of thermal mass, we can actually use normal building materials and integrate into them phase change materials that can add thermal mass. Some of the ways we can do that is to put it in normal building materials like wallboard or ceiling tile or floor tile. But it's not enough just to put the material there. We can't just have the store. We have to have some way to control it, some way to utilize it. And one of the goals in the research we're doing on PCM integration into building materials is to determine the effects of PCM location on its operation. For instance, does it work better in the walls? Does it work better in the ceilings? Does it work better in the floors? Are there ways we can have the air conditioning system direct airflow to intentionally cool or heat up a section of PCM containing material to help us utilize that store? Right now, typically what's done is you put in as much PCM as you can and you cool it as much as you can and you try to store as much energy as you can for the next cycle. And that's what's happening here. If you look here, each of these blue lines are actually different charge rates. We change the temperature at which we're charging the PCM, and as a result, we can charge it more. But we actually have much more PCM that we're actually using, and we just charge as much of it as we can. And what we'd like to do is simplify this some so that we can actually charge it intentionally at a rate that we understand and we know, so that we don't have to put in more PCM material or more phase change material than we need. So we're working on that. We're also looking at testing the impact of PCM-aware systems that can intentionally charge or discharge sections of PCM-containing material at particular points in time. Some of the issues that we run into as we look into this are, how do we know when the material is charged? If I simply put wallboard on the wall, how do I know when it's charged? How do I know when it's been cooled enough? And those are some of the issues that we're looking at now to develop some method of determining charge status. But we're also looking into integrating controls for the HVAC system that can actually make use of knowledge of the PCM status and communicate with the grid as to what energy availability is. There are some issues with PCM integration. One is control. It's really a big deal. It's difficult to control the charge status. Another way we can do it is we can use active PCM-based thermal storage. Now, these are easy to control. We actually can design systems that we use as an adjunct to an HVAC system that we can charge and discharge, and it becomes part of the AC system, and nobody's really needs to be aware that it's there. In the previous case, where we're looking at putting PCM in the wallboard and the ceilings or in the other building materials, we actually have to intentionally change the temperature of the environment to charge or discharge it. And so we have to have this variable temperature range under which the building operates. And there's difficulties with that. For instance, if I want to charge the PCM, I have to push the temperature down. And you saw on the last slide where we had to push the temperature down, say 4 degrees below the PCM freeze point. But when we do that, people in the building may not be very comfortable. We're counting on the building being a commercial building that's vacant at night so that we can push that temperature down and no one's concerned. But if it's a building it's actually being used more frequently or day in, day out, that might pose a problem in trying to store that energy. In this case, we can store the energy completely independent of the HVAC environmental system. It does not, the internal environment of the building doesn't need to have any change associated with it. So I'm very interested in active PCM-based thermal storage, and that's what I'm working on now. And some of the goals with this project is to develop simplified models that we can use to optimize thermal stores, and not just to optimize them, but to come up with a parametric design process where we can just call out a few different parameters, and using those parameters alone, get a very good approximation of the thermal store that we actually need. One of our goals for that thermal store is that we have an 80% energy recovery over a 2-hour period. We've seen a lot of research where people are very concerned about how quickly they can recover the energy placed in a thermal store. And my response to that is it only needs to be fast enough. It doesn't have to be instantaneous. 2-hour period is fine. And we look at peak energy use. It's actually over a 5 to 2 hour period. So 2 hours as a minimum recovery time for 80% of the energy in the store is actually very useful, a very useful design goal. So right now, I'm currently working on the model, and the model's essentially done, and we'll see some results from the model. And I'm also working on prototypes for the thermal stores. The first one that I'm working on right now is a small scale. It'll be about 1 meter tall. It'll have about 1.5 kilowatt hours of storage, and we'll be testing it, comparing the results to the model. We're also building a full-scale model at the Facade Thermal Lab here at the University of Texas School of Architecture, and that's going to be a 6.25 kilowatt hour model. And hopefully we'll end up with design guidelines that can be used for very simple design guidelines that don't require somebody run a large numeric model. The store that we settled on for these two projects are what I'm terming as a reverse tube and shell design, because most of the cases where I've seen tube and shell designs, what happens is we take a tank of PCM and we run tubes through it. And as we run the heat transfer fluid through the tube, we're able to transfer energy. But the problem is, if you want to increase the performance, you have to add more tubes. If I add more tubes, I have less PCM. And it becomes a cycle where you're not able to fully utilize the space available. In this case, instead, we're going to take the PCM and we're going to pack it in PVC tubes. And then we're going to pack those inside of a cylinder. And we've determined optimal schemes for packing of the tubes in the cylinder. And now the water, the heat transfer fluid actually flows around in a one-pass system through the thermal store unit. And you'll see that on the next slide. I'll show a little clearer. But the connection points of where the tubes come together form natural pathways for the heat transfer fluid to traverse. We chose tubes rather than spheres because spheres don't have as good a packing ratio. They're about 74% theoretical maximum, whereas tubes we can get up to 90%. In reality, there's a loss. We get about 82% in this. And also, it's much easier to change the performance level of a tube-based system. If I need better performance, I just put smaller tubes. Surface area to volume goes up, transfer rates go up, performance goes up. On spheres, to make smaller spheres and pack them with PCM is expensive. Make small tubes smaller is very inexpensive. It's very easy. We're using a phase change material what we're using for a phase change material is a light paraffin called tetradecane. It's very similar to a light fuel oil. It has a freezing temperature we want of 5.6 degrees C, which is suitable for AC conditions, and it has a fairly large thermal storage rate of 220 kilojoules per kilogram during the phase change. Now, one thing about this model, it does require a vertical orientation, and that's because we design them to have a low velocity flow, and that's critical because if we didn't do it with a low velocity flow, let's say one of the tubes got shifted and it made a larger area for water to flow through, water would naturally want to flow that way. But by keeping it laminar and keeping it low velocity flow and a relatively high temperature gradient, the buoyancy effects actually dominate, and we don't have to worry about short circuiting. The tubes can be loose and it won't make any difference. So the numeric model, based on that design, is deals with advection, convection, and conduction through the heat transfer fluid, the PVC shell, and the PCM thermal storage material. And what we've done is, because the way these push together, we end up with these triangular shaped spaces. We're actually modeling those as triangular pipes. So it's just as if we're running fluid through a triangular pipe and we're doing heat transfer as a result. And that actually works out pretty well. It turns out, when we get to the model, you'll see that this particular design is not convection limited, it's conduction limited. So we can actually change the convection coefficient dramatically and have very little effect. But this looks like it works pretty well, and I'm hoping to validate it when we do the physical model. And by doing this particular design, we end up with these diamond-shaped units that are all identical. And the interfaces that are drawn in red there, they actually are adiabatic interfaces. They're all the same. We're not going to have any heat transfer across them. So we really only need to look at this one element and then multiply it by 6 and times the number of tubes, and we get our total thermal performance capacity. Now, this is the results of the numeric model run for both the small-scale prototype and the full-scale prototype for the facade thermal lab. And let me explain what you're looking at here, because it does. I see it easily, but you might not. What this is time. And so as time goes by, I'm recording the water temperature from top to bottom in the thermal store. And this is the location from the top. So 0 is the top, and then all the way at the end is the bottom. And then this is the temperature in the store. So if you took a slice this way of this graph, what you would have is, at that very specific moment in time associated with wherever time point you were at, you would have a plot of the water temperature, the heat transfer fluid temperature from top to bottom in the tank. And what you can see here is that as the heat transfer fluid passes through over time, we end up depleting some of the PCM. We actually melt the PCM, and it has no more thermal energy stored to give us. And then you have a curve as it drops down. And this is what it looks like at the very, what this looks like plotted. And this is the water temperature output from the initial point all the way up to the end. And what you see here for this, what the model's telling us is that for the prototype design, we actually do get 80% of more than 80% of the total, we get 78% of the latent heat recovery energy out of that store in just a 2-hour period, and we get it out at a useful temperature. The temperature range varies from 5.6 degrees C, which is the freezing point of the PCM, to 6.1 degrees C as it climbs as we consume the thermal store. So we're getting results exactly what we hope to get. And this tells us that it is very suitable for air conditioning applications, that we can use this to offset some of the electric normally used for air conditioning. The full-scale one is the same thing. The full-scale one isn't quite as efficient because we changed the tube size. That's what really the two critical points of these that control its performance is the diameter of the PCM encapsulation and the flow rate of the heat transfer fluid. So this one's not as good because I changed the tube size. I didn't want to have to fill 887 tubes. I only want to fill 400 tubes. And so I'm using a slightly larger encapsulation system. And that's why the output temperature is a little higher too, 6.7. This actually drops to below 6 if I put in the same tube size that I have in the prototype model. And here's an example application of where we think this could be used. If we go to retail pricing scheme based on dynamic pricing, you'll see that the peak time is actually a very narrow period of time. This is 5 hours. And if the dynamic retail pricing is communicated to our control system can make a decision based on how much money it wants to spend on when it kicks in the thermal store and when it bypasses the thermal store and runs the chiller. Another application for this that we're also investigating, but we're very early stages, is integrating into residential appliances like a refrigerator, PCM material, because residential refrigerators account for 13% of your residential energy use. So if we can control that, if we can shut that off during the day, we can actually have an impact that might actually prove useful as well. So we're looking at integrating PCM into a refrigerator that is also made grid aware and can take cues from the grid on when to stop running its compressor and run off of the PCM built into the device. And that's it for me. Any questions? You have to wake up now. Yes. Well, good.
Cost significant in these systems, and if so, have you looked at the pressure drop for your different configurations? I'm assuming you get more pressure drop with the reverse tube design.
I don't think we're going to get any pressure drop because the velocity is so low. I mean, we're talking the velocity through the tank is a centimeter a second, and the cross-sectional area is actually quite large. It looks like it's very small areas, but the total cross-sectional area is actually quite large. So I don't expect us to have much through that. Through the rest of the piping, possibly, but through the tank, I don't expect much at all. But we'll find out. It's a good question, and when I run the small-scale experiment in the next week or two, I'll take a look at that.
So you go back to your slide, just a couple slides back. Hey, that one right there, next one. So you talk about for the commercial customers, you consider I'm asking, so you mentioned for the commercial customers that you consider the effective peak prices, but I know, so for example, in Austin, there's a thermal energy storage rider for large commercial customers, and it actually has some more to do with demand charges. So basically, it's encouraging you to use thermal storage to reduce your demand.
Yeah.
So I guess it's like, so how do you consider for your control system basically reducing the peak demand over the day, ignoring prices, really? I don't know.
Well, the reason why I bring this up is because the dynamic retail pricing actually gives a strong cost incentive to implement this. Even though they're not very expensive, you still need a strong cost incentive. But that's a very good point, and some utilities are different. But if you can reduce your peak demand, you get a lower rate. I mean, your service costs are a lot lower, so that's something to look at too.
In the case of Austin Energy, I think the interesting thing is that so the thermal energy storage rider, the demand charge goes from, I think, more than $10 per kilowatt to $0 per kilowatt.
For having thermal storage?
For off-peak demand. Your off-peak demand charge goes to zero. And so if you were to do all of your cooling, for example, at night, you could have potentially very low demand charge.
You know, I would like to talk to you about that later because I'm working on a paper and I would like to integrate something about that. So if we can have a minute later, that'd be good. I'm off the hook already. Thank you.
All right. Thank you very much. So thanks for attending, and next week, I think it's Dr. Metcalf. Is that right? Or is that 2 weeks from now?
I think it's Dr. Metcalf. Yeah, and 2 weeks from now is Chevron Energy Solutions, right?
Right.
Yeah,
right.
You got it.
So anyway, in case you don't know, you should Google Dr. Metcalf and find out what a famous person he is. So you can come back. All right. Thanks again.